Alright, so now we're looking at the scenario where we need to solve for the force acting on a parallel current carrying conductor, which is in the presence of two other conductors rather than just one other conductor. It's no more difficult than doing the two parallel current carrying conductor one. It's just that it takes a little bit more time because we need to use that same equation twice. Okay, so if we read through this question, we'll draw the diagram of what this question is actually saying, and then we'll use our parallel current carrying conductor equation twice to solve for the force on the initial conductor. Right, so we've got a conductor carrying 2 amps down the page. So here's our conductor carrying 2 amps down the page. Placed 3 millimeters to the left of a conductor carrying 3 amps up the page. So it is 3 millimeters to the left of a conductor carrying 3 amps up the page. So our distance in there is 3 millimeters. And that same conductor is placed 4 millimeters to the right of a conductor carrying 1 amp down the page. So here's our current carrying conductor carrying 1 amp down the page. And 4 millimeters. Okay, so this is why I told you earlier that we really shouldn't use the words attractive or repulsive when talking about the force on a specific conductor. Because if you look at these two conductors here, they've got current going in the same direction. They are like currents, so we learned that like currents attract. So this would exert an attractive force between those two conductors. These ones here, we've got currents going in opposite directions, so they're unlike currents, and they're going to produce a repulsive force. So we've got attractive between these two, repulsive between these two, and you'd be tempted to say that attractive and repulsive are opposite, kind of like up and down are opposite, so we take the forces away from each other. Okay, but if you have a look at what happens to the middle conductor, if these two are attractive, the middle conductor will move towards the conductor on the left, so it's moving towards the left. If this is repulsive, again the middle conductor will move away from this conductor here, i.e. it's moving to the left. Okay, so if we use attractive or repulsive, you might be tempted to take them away from each other, when in reality, the attractive force causes it to move left, the repulsive force causes it to move left, so actually add the forces together. Okay, now solving for the magnitude of force on this initial conductor here. Alright, so we use our parallel current carrying conductor equation, and we usually denote it as, conductor 1, conductor 2, conductor 3. So firstly, I want to figure out the force between conductors 1 and 2, and we call that F1, 2. Okay, so that's just going to be from our parallel current carrying conductor equation, K, I1, I2, L over D. So 2 times 10 to the minus 7, times our two currents of 1 and 2. So 1 times 2. Each conductor is 1 meter in length, as given in the question, so times 1 meter. And the distance between them here is 4 millimeters, so 4 times 10 to the minus 3. If we work this out, it should come out to be 1 times 10 to the minus 4 newtons, including our direction of left. Okay, so I've figured out the force of this conductor here acting on the central conductor, which is what I want to try and figure out. But that would be fine if there was only 2, but there's a third one on the opposite side of our initial conductor. So we also need to take into account the magnetic field from the current flowing through this conductor is going to interact with the magnetic field of the conductor going through our original conductor. Okay, so we'll call this the force between the second and the third conductor, so we call it F2, 3. Okay, so the force of, actually we might call it F3, 2. So the force of the third conductor on the second conductor. Same equation, K, we'll call this I2, I3, L over D. So 2 times 10 to the minus 7, multiplied by our two currents of 2 times 3, our length of 1 meter, and our distance of 3 millimeters, 3 times 10 to the minus 3. Okay, now if I figure all this out, that'll come out to be 4 times 10 to the minus 4 newtons left. Okay, left because we said these are unlike currents, so there's going to be a repulsive force. So force on the second conductor will be towards the left, which is away from that third conductor. So we've got two forces acting to the left. So we can just say F2, so the force on 2, or you might want to call it the net force or something like that. So F net is just the sum of those two things. Always show that step. You know, it's such a simple step that so many students actually leave it out. Okay, so it's 1 times 10 to the minus 4 plus 4 times 10 to the minus 4, which equals 5 times 10 to the minus 4 newtons left. Okay, so it's no harder than just the 2 parallel current carrying conductors, it's just that you have to do it twice, so it takes a little bit longer. Alright, so most of the time you'll be asked about the central conductor, but let's just say you're asked about one of the other two. Okay, so part B is saying find the resultant force on the leftmost conductor, so it's asking about this conductor here. Now in the previous question we already figured out the force between these two, so conductor 1 and conductor 2. And we figured out that the value of the force between those two conductors is 1 times 10 to the minus 4 newtons. All right, however, what we'll do is we'll change the direction because we're now looking at conductor 1, okay, rather than conductor 2. So this was an attractive force. So conductor 1 should experience a force towards the right, okay, towards conductor 2. Now we also need to figure out what is the effect of conductor 3 on conductor 1. Okay, so we can call that, you know, F3, 1. And again, same equation, K, I1, I3, L over D. So 2 times 10 to the minus 7 times 2 times 3 times our length of 1. Now the distance of separation, now we need to assume here that the wire in the middle, I suppose, is infinitesimally thin. Okay, it has no, you know, let's say X dimension or something like that. It's an infinitesimally thin wire. So the distance between wire 1 and wire 3 is just the sum of those two distances, 4 millimeters, plus 3 millimeters, so we get 7 millimeters. So 7 times 10 to the minus 3. And if you quickly do that, the force should come out to be around about 8.6 times 10 to the minus 5 newtons. So 8.6 times 10 to the minus 5 newtons. Now the direction, these are unlike currents. Unlike currents repel. So the force on conductor 1 will be away from conductor 3, which is towards the left. Okay, so then if we figure out the net force on conductor 1, so force on 1, or again F net or something like that, just the sum of these two forces. Now they're in opposite directions, so we'll use positive for the big one, negative for the smaller one, and essentially subtract them from each other. Okay, so 1 times 10 to the minus 4 minus 8.6 times 10 to the minus 5, and that'll come out to be around about 1.4 times 10 to the minus 5 newtons. Okay, and the direction is the direction of the bigger number, so in this case it's going to be right. Easy.